Hi guys, this is the EdExcel A-Level Maths Paper 2 from the October 2020 series. So let's get straight into it. Question number 1. The table below shows corresponding values of x and y for y equals the square root of x over 1 plus x. The values of y are given to 4 significant figures. We have our x values here, our y values here, and for part A we have to use the trapezium rule with all the values of y in the table to find an estimate for the integral of the square root of x over 1 plus x with respect to x in between 0.5 and 2.5, giving our answer to 3 significant figures. And if you take a look in the formula book, the trapezium rule is shown highlighted here. The integral of y with respect to x in between a and b, that's approximately 1/2 h multiplied by our first y value plus our last y value plus 2 lots of the y values in between, where h is equal to b minus a over n. Our first step would be to label our y values. We have y0, y1, y2, y3 and y4. When we come to use the trapezium rule, we first of all need to find out the value of h. So for part A, h is equal to 2.5 minus 0.5 divided by 4. So if we work this out, 2 divided by 4, that's 0.5. And knowing the value of h, we can now use the trapezium rule. So we have the integral between 0.5 and 2.5 of x over 1 plus x square rooted, like so. And if we approximate this using the trapezium rule, we have 0.5 over 2, and then we multiply this by our first y value, 0.5774. So we have 0.5774 plus 2 lots of the middle y values. So we have 2 lots of 0.7071 plus 0.7746 plus 0.8165, and then we have our last y value, 0.8452. So we add on 0.8452, and if we work all of this out, we have over here, using our calculator, 0.5 over 2 lots of 0.5774 plus 2 lots of 0.7071 plus 0.7746 plus 0.8165 plus 0.8452. So working all of this out, it turns out we get 1.50475. And giving our answer to three significant figures, we see we have 1.50 to three significant figures. And now for part B of the question, using our answer to part A, we have to deduce an estimate for the integral in between 0.5 and 2.5 of the square root of 9x over 1 plus x with respect to x. Well, here for part B, we would have to use the laws of surds. So, we have the integral of 9x over 1 plus x square rooted in between 0.5 and 2.5 with respect to x, and using the laws of surds, we can rewrite this as the square root of 9 multiplied by the square root of x over 1 plus x square rooted. Okay? And of course, we're integrating this in between 0.5 and 2.5 with respect to x. And the square root of 9, that's 3. So if I take this 3 outside the integral, we have over here 3 lots of the integral between 0.5 and 2.5 of the square root of x over 1 plus x. Okay? With respect to x. So if we work this out, we have over here 3 times by. Now I would like to use my answer which is not rounded, so I will use the 1.50475. So working this out, so multiplying this by 3, it turns out we get over here 4.51425. And if I give this to three significant figures, we have 4.51 to three significant figures. And now for part C of the question, given that the integral of the square root of 9x over 1 plus x with respect to x in between 0.5 and 2.5 is equal to 4.535 to four significant figures, we have to comment on the accuracy of our answer to part B. So we see over here that the actual integral is 4.535 to four significant figures, and therefore if we compare this result here with this result here, we can round both of them to 4.5, so therefore the answer to part B is accurate to two significant figures. Question number 2. Relative to a fixed origin O, the points P, Q and R have position vectors P, Q and R respectively, and given that P, Q and R lie in a straight line, and Q lies 1/3 of the way from P to R, we have to show that Q is equal to 1/3 of R plus 2P. So it will be a good idea to first of all sketch the situation. So we've got this straight line over here, we've got this point P, we've got this point R over here, and Q is 1/3 of the way from P to R. So somewhere over here we have the point Q. Now we wish to show that Q is equal to 1/3 of R plus 2P, and from these two statements here we can say that PQ is equal to 1/3 of PR. Okay. Now, the vector PQ, that's equal to Q minus P. Okay. And the vector PR, that's equal to R minus P. And we simply have to rearrange for Q. So if I multiply the 1/3 into the bracket, we have 1/3 R minus 1/3 P, and this is equal to Q minus P. And if I add P to both sides, we see here that Q is equal to 1/3 R plus 2/3 P. And if I factorize out a 1/3, in conclusion, Q is equal to 1/3 of R plus 2P. Question number 3 for part A. Given that 2 times by the log of 4 minus x is equal to the log of x plus 8, we have to show that x squared minus 9x plus 8 is equal to 0. So for part A, we begin with the 2 times by the log of 4 minus x, and this is equal to the log of x plus 8. If I power slide this 2 to the top over here, we have the log of 4 minus x squared, which is equal to the log of x plus 8. If I anti-log both sides, we see over here effectively the logs disappear. We have 4 minus x all squared, which is equal to x plus 8. And if I expand out 4 minus x all squared, we end up with x squared minus 8x plus 16, and this is equal to x plus 8. And in conclusion, we see x squared minus 9x plus 8 is equal to 0. For the first part of part B, we have to write down the roots of the equation x squared minus 9x plus 8 equals 0. So for the first part of part B, we have x minus 8 lots of x minus 1 equals 0. That's just factorizing this quadratic, and therefore in conclusion x is equal to 8 or x is equal to 1. And for the second part of part B, we have to state which of the roots in the first part of part B is not a solution of the equation 2 times by the log of 4 minus x equals the log of x plus 8, giving a reason for your answer. Well, clearly, if I substitute in x equals 8 into this equation here, we have the log of 4 minus x. So we would have a log of a negative. So let's just write that down. We see that when x is equal to 8, 2 times by the log of 4 minus 8 cannot be found. We have a log of a negative, and therefore x equals 8 is not a solution. Question number 4. In the binomial expansion of a plus 2x to the power of 7, where a is a constant, the coefficient of x to the 4 is 15120. We have to find the value of a. Well, if we use our formula for the binomial expansion, that's shown highlighted here, a plus 2x to the power of 7, that will equal 7 choose 0 multiplied by a to the 7 lots of 2x to the 0 plus 7 choose 1 lots of a to the power of 6 lots of 2x to the power of 1 plus 7 choose 2 a to the power of 5 2x to the power of 2 plus 7 choose 3 multiplied by a to the power of 4 multiplied by 2x cubed plus 7 choose 4 a to the power of 3 multiplied by 2x to the power of 4. And we've got extra terms as well. We need to consider the coefficient of x to the 4, and the coefficient of x to the 4 can be obtained using this term over here. And we know that the coefficient of x to the 4, that's 15120. So in other words, we have 7 choose 4, a to the power of 3, 2x to the 4, which will equal 15120 x to the 4. So if we tidy up the left hand side, we have here 7 choose 4 multiplied by the 2 to the power of 4. So we have 560 a cubed in terms of numbers. So we have 560 a cubed, and this is equal to 15120. We therefore see that a cubed, that will equal 15120 divided by this, which is 27, and cube rooting both sides, we can see here a is equal to 3. Question number 5. The curve with equation y equals 3 times by 2 to the power of x meets the curve with equation y equals 15 minus 2 to the power of x plus 1 at the point P. Find using algebra the exact x coordinate of P. Well, we have to solve this equation with this equation simultaneously, and we can do that by setting these equations equal to each other. So we have 3 times by 2 to the power of x, which is equal to 15 minus 2 to the power of x plus 1. And we can use the laws of indices on the right hand side. So we have 3 times by 2 to the power of x. This is equal to 15 minus 2 times by 2 to the power of x. Of course, 2 is the same as 2 to the power of 1, and adding the powers, 2 times by 2 to the power of x is 2 to the power of x plus 1. So now we can gather all the terms involving an x on one side, everything not involving an x on the other side. So taking this 2 times by 2 to the x on the left hand side, we have 3 times by 2 to the power of x plus 2 times by 2 to the power of x, which is equal to 15. And we can factorize out a 2 to the power of x. So we have 2 to the power of x lots of 3 plus 2, which is equal to 15. So we have 5 multiplied by 2 to the power of x, which is equal to 15. Dividing both sides by 5. 2 to the power of x, that's equal to 3. And we want to find the exact x coordinate of P. So solving for x is equal to log base 2 of 3. 2 to the power of x is equal to 3. Question number 6 for part A. Given that x squared plus 8x minus 3 over x plus 2 is equivalent to ax plus b plus c over x plus 2, where x is a real number and x doesn't equal minus 2, we have to find the values of the constants a, b and c. So for this question, we can multiply both the left hand side and the right hand side by x plus 2. So for part A of the question, we begin with the x squared plus 8x minus 3 on the bottom. We've got the x plus 2, and this is equivalent to ax plus b plus c over x plus 2. Multiplying both sides by x plus 2 on the left hand side, we end up with x squared plus 8x minus 3, and on the right hand side we have ax plus b lots of x plus 2 plus c. And to find the values of a, b and c, we can compare coefficients. So we can compare coefficients to find the values of a, b and c. So if we compare the x squared terms, you can see on the left hand side we have one of them, and on the right hand side ax times by x gives an x squared term. So we have 1 which is equal to a. Of course a is equal to 1. If we compare the x terms on the left hand side, we have 8 of them, and on the right hand side ax times by 2 gives an x term, so we have 8 equals 2a, and also the b multiplied by the x also gives an x term. So we have 8 equals 2a plus b. We know that a is equal to 1, so we have 8 equals 2 times by 1, which is 2, plus the b. B is equal to 6. We can now compare the number terms. If we compare the number terms, on the left hand side we have minus 3 of them, and on the right hand side we have b times by 2, that gives 2b, that's a number term, so we have minus 3 equals 2b, and then we also have the plus c. We know that b is equal to 2, so we have minus 3 equals 2 times by b, so 2 times by 6, that's 12. So we have minus 3 equals 12 plus c, subtracting 12 from both sides, c is equal to minus 15. Knowing the values of a, b and c, we can therefore conclude x squared plus 8x minus 3 divided by x plus 2, that's equivalent to x plus 6 minus 15 over x plus 2. For part B of the question, hence using algebra integration, we have to find the exact value of the integral from 0 to 6 of x squared plus 8x minus 3 over x plus 2 with respect to x in between 0 and 6, giving an answer in the form a plus b times the natural log of 2, where a and b are integers to be found. So we wish to find the integral from 0 to 6 of x squared plus 8x minus 3 divided by x plus 2 with respect to x. So this is equivalent to the integral from 0 to 6 of x plus 6 minus 15 over x plus 2 with respect to x. So if we integrate the x, we end up with 1/2 x squared. If we integrate the 6, we end up with 6. And if we integrate the minus 15 over x plus 2, we have minus 15 times by the natural log of the mod of x plus 2. So we wish to evaluate this in between 0 and 6. So for the upper limit, we have 1/2 times by 6 squared plus 6x. So here, sorry, we had 6x. So we have 6 times by 6 minus 15 times by the natural log of the mod of 6 plus 2. For our lower limit, of course, we have 0 plus 0 minus 15 times by the natural log of the mod of 0 plus 2. So we have here 1/2 of 36, which is 18, plus another 36, that's 54. So for our first bracket, we have 54 minus 15 times by the natural log of 8, because 6 plus 2, that gives the 8. For this bracket, we have minus 15 times by the natural log of 2. So we have 54 minus 15 times by the natural log of 8 plus 15 times by the natural log of 2. Of course, minus and a minus give the plus. And if you look at our answer, we have to express this in the form a plus b times the natural log of 2. And with this 8, we can rewrite the 8 as 2 cubed. So we have 54 minus 15 times by the natural log of 2 cubed plus 15 times by the natural log of 2. And if we power slide this 3 to the front, we have 54 minus 15 times by 3, which is 45. So we have minus 45 times by the natural log of 2 plus 15 times by the natural log of 2. So tidying all this up, we have 54 minus 30 times by the natural log of 2. In conclusion, a is equal to 54, b, that's equal to minus 30. Question number 7. We've got figure 1 over here, which shows a sketch of the curve C with equation y equals 4x squared plus x over 2 times by the square root of x minus 4 times by the natural log of x, where x is greater than 0. And for part A, we have to show that dy over dx is equal to 12x squared plus x minus 16 root x over 4x root x. Now, it may be a good idea to rewrite the square root of x as x to the power of a half. The reason for that, it will become easier to differentiate. So, for part A of the question, if we rewrite what y is, we have y equals 4x squared plus x divided by 2x to the power of 1/2 minus 4 times by the natural log of x. And we can use the laws of indices to simplify all this. Of course, 4x squared plus x over 2x to the half, that's the same as 4x to the power of 2 divided by 2x to the 1/2 plus x over 2x to the 1/2 minus 4 times by the natural log of x. And if we tidy all this up, 4 divided by 2, that's 2. And x squared divided by x to the half, if I subtract the powers, 2 minus 1/2, that's 3 over 2. So we have 2x to the power of 3 over 2. Now here, in terms of the numbers, we have 1/2. And x divided by x to the half, again subtracting the powers, 1 take away 1/2, that's 1/2. And then we still have minus 4 times by the natural log of x. So when we come to work out what dy over dx is, we can simply use standard derivatives. So dy over dx, that's equal to, well, if I differentiate 2x to the 3 over 2, times by the power, subtract 1 from the power, we have 3x to the power of 1/2. Differentiating 1/2 x to the half, multiplying by the power, and then subtracting 1 from the power, we have 1/4 x to the minus half. And differentiating minus 4 times by the natural log of x, we end up with minus 4 over x. So if we were to tidy this up a little more, we can see here that, well, we'll leave the 3x to the half alone. The 1 over 4 x to the minus 1/2 we can rewrite as 1 over 4x to the power of 1/2, and then we subtract off 4 over x. Now at this point we can write each of these terms over a common denominator. But before we do that, let's convert these x to the halves into third form. So we have 3 times by the square root of x plus 1 over 4 times by the square root of x minus 4 over x. And if we pay attention to what we wanted to show, you'll notice at the bottom we have a 4x times by the square root of x. And we can rewrite every term such that we have that denominator. So if we do that, for this term we want the denominator to be 4x times by the square root of x, and therefore on the top, well, we still need this 3, and we still need this root x, so what would cancel with the bottom will be 4x times by the square root of x. Let's just extend this line. So it's as though this 4x times by the square root of x cancels on the top and the bottom, leaving us with 3 root x. And this 1 over 4 root x, well, if we do the same thing again, we want the denominator to say 4x times by the square root of x. And the only way we can get that result here is by having an x at the top. It's as though this x cancels with this x. And then for this 4 over x, well, we want the denominator to say 4x times by the square root of x. And for us to get a 4 at the top. If I have a 4 at the bottom, we need a 16 at the top. 16 divided by 4 gives the 4. And we need a root x over here, which will cancel with this root x, leaving us with 16 over 4x, which simplifies to 4 over x. So we have this result over here. And now we can combine the fractions because we have a common denominator. So on the top we have 3 times by root x times by 4x times by the square root of x plus x minus 16 times by the square root of x. And on the bottom we have 4x times by the square root of x. And therefore, if we tidy all of this up, on the top, well, we have 3 times by 4, that's 12. And then we have the x over here. Now, root x times by root x, that's just x. So we have x times by x, which is x squared. And then we have plus x minus 16 root x. On the bottom, we have the 4x times by the square root of x, and this is what we wanted to show. Now for part B of the question, the point P shown in figure 1 is a minimum turning point on C. So here we have a minimum turning point. And we have to show that the x coordinate of P is a solution of x equals 4/3 minus root x over 12 to the power of 2 over 3. Now whenever we see the word minimum turning point, the word turning point suggests to us that dy over dx is equal to 0. And if we write that down, that will help us show this solution here. So, we know what dy over dx is, and therefore, if we set dy over dx equal to 0, we have this result here, 12x squared plus x minus 16 root x over 4x times by the square root of x is equal to 0. So with this we can tidy all this up. So multiplying through by 4x times by the square root of x, we have 12x squared plus x minus 16 times by the square root of x. Now, if we take this to the other side, we have 12x squared, which is equal to 16 root x minus x. And with this we can now divide by root x on both sides. So if we do that, we have 12x squared divided by root x, and this is equal to 16 root x divided by root x minus x over root x. So if we tidy this up a little more, we first of all notice this root x cancels with this root x, so we have here 12x squared. On the bottom we have x to the power of 1/2. It might make our lives a bit easier if we rewrite the square root of x as x to the half, and this is equal to 16 minus x over x to the power of 1/2. And now, subtracting the powers, we have 12x to the power of 2 minus 1/2, which is 3/2. And this is equal to 16 minus x to the power of 1 take away 1/2, which is 1/2. And if we divide both sides by 12, we have x to the power of 3/2, which is equal to 16 divided by 12, which is 4/3, minus x to the power of 1/2 divided by 12. So, to get x by itself, we can raise both sides to the power of 2/3. So we have x equals 4/3 minus x to the power of 1/2 divided by 12 to the power of 2/3. And this is exactly what we wanted to show, because from here you can see in conclusion x is equal to 4/3 minus root x, which is the same as x to the power of 1/2, divided by 12 raised to the power of 2/3. For part C of the question, we have to use this iteration formula, xn plus 1 equals 4/3 minus square root of xn/12 to the power of 2/3 with x1 equaling 2 to find the value of x2 to 5 decimal places, and then the x coordinate of p to 5 decimal places. So, if we use the iterative formula given to us for part C of the question, we have xn plus 1 equals 4/3 minus xn square rooted divided by 12 raised to the power of 2/3. And we know that x1 is equal to 2. So x2, that's equal to 4/3 minus the square root of x1/12 to the power of 2/3. So if we work this result out, we type into our calculator and press equals, so our answer function is storing 2. So with this, we type in this over here, replacing x1 with answer. So we have 4/3 minus the square root of answer over 12 to the power of 2/3. So this tells us the value of x2. So the value of x2 is equal to 1.1389, etc. Which to 5 decimal places, let's work this out. If we work this out, we have to 5 decimal places 1.1389, let me work this out, 1.13896 to 5 decimal places. So for the next part of the question, we have to find the x coordinate of p to 5 decimal places. So to do this, we need to find out what x3 is. So x3, that's equal to, press equals again, we have 1.156928424. We can find out what x4 is, so working out x4, we have over here 1.1569284 156, 494, 678, x5, that's equal to 1.156, 505, 095, x6, that's equal to 1.156, 504, 845, and what you'll notice over here, x5 and x6 both round to the same value after 5 decimal places. So here we will assume we have convergence. So we can therefore conclude the value of x is equal to 1.15650. Question number 8. A curve C has equation y equals f of x, and given that f dash of x is equal to 6x squared plus ax minus 23, where a is a constant, the y-intercept of C is equal to minus 12, and x plus 4 is a factor of f of x, we have to find in simplest form f of x. So we know what f dash is. Now, here, if we know that the y-intercept of C is minus 12, this suggests to us that f of 0 is equal to minus 12. When x is 0, y is minus 12. And if x plus 4 is a factor of f of x, that suggests to us that f of minus 4 is equal to 0. That's using the factor theorem. Now, we can actually find out a general form of f of x. And we can do that by recognizing that f of x is equal to the integral of f dash of x with respect to x. So we would have to integrate f dash of x to find f of x. So we need to integrate 6x squared plus ax minus 23 with respect to x. And if we do this, add 1 to the power, divide by the new power, the integral of 6x squared is 2x cubed, and if we integrate ax, remember a is just a constant, it's just a number, add 1 to the power, divide by the new power, the integral of ax is equal to 1/2 ax squared. And if we integrate minus 23, we get minus 23x. And don't forget, we have a constant of integration. We'll call that constant of integration capital A. Now, using what we have over here, f of 0 equals minus 12. Substituting 0 into here, we have 2 lots of 0 cubed plus 1/2 lots of a lots of 0 squared minus 23 lots of 0 plus a. This is equal to minus 12. So therefore a is equal to minus 12. And knowing the value of a, we can see that f of x is equal to 2x cubed plus 1/2 ax squared minus 23 x minus 12. Now we can find out what a is by using f of minus 4 equals 0. So, using f of minus 4 equals 0, we have 2 lots of minus 4 cubed plus 1/2 a lots of minus 4 squared minus 23 lots of minus 4 minus 12. This is equal to 0, and that's through the factor theorem. So here, if I work this out, gathering everything involving a number, we have minus 48 plus 8a equals 0, 8a is equal to 48, and therefore a is equal to 6. And knowing the value of a, we can therefore conclude f of x is equal to 2x cubed plus 3x squared minus 23x minus 12. Question number 9. A quantity of ethanol was heated until it reached boiling point, and the temperature of ethanol, 30 degrees C, at time t seconds after heating began, is modelled by the equation theta equals a minus b e to the minus 0.07 t, where a and b are positive constants. And given that the initial temperature of the ethanol was 18 degrees C, and after 10 seconds the temperature of the ethanol was 44 degrees C, we have to find for part A a complete equation for the model, giving the values of A and B to 3 significant figures. So we begin over here for part A with our equation theta equals A minus BE to the minus 0.07 T. Now, we were told the initial temperature was 18 degrees C, so when T is equal to 0, theta is equal to 18. So, substituting everything in, we have 18 equals A minus B E to the power of 0. So we have 18 equals A minus B. We also know that after 10 seconds the temperature of the ethanol was 44 degrees. So when T equals 0, theta is equal to 44 degrees. So we have 44 equals A minus BE to the power of 10 times by minus 0.007, which is minus 0.7. So we can rewrite this to help us find the value of A and B. Essentially, we've got a simultaneous equation to solve. So if I rewrite this, I have 44 equals A minus B over e to the 0.7. Of course, something raised to a negative power is 1 over something. And now if I multiply through by e to the 0.7, we have 44 e to the power of 0.7 equals A e to the 0.7 minus B. And if I call this equation 1 and this equation 2, we can subtract those equations to eliminate the B variable, which will help us to find A. So if we do equation 2 minus equation 1, we have 44e to the 0.7 minus 18 on the left hand side, and this is equal to AE to the 0.7 minus A, and then minus B minus minus B, the B's cancel out. So on the right hand side we can factorize out an A. We have A lots of e to the 0.7 minus 1. So we have 44 e to the 0.7 minus 18 equals A lots of e to the 0.7 minus 1. And if we rearrange for A is equal to 44 e to the 0.7 minus 18 divided by e to the 0.7 minus 1. So if we work this out, we have over here 44 e to the power of 0.7 minus 18 divided by e to the 0.7 minus 1. It turns out we get 69, 69.647. So therefore, in conclusion, the value of A is equal to 69.647, etc. From which we can find out what B is. Well, let's just give A to 3 significant figures. We can find out what B is by substituting into this equation here. So if we store this into A before anything, we see here that 18 is equal to 69.6, etc. minus B. So from this we can find out the value of B. So B is equal to this value minus 18, which is 51.647, etc. And to 3 significant figures, B is equal to 51.6. So let's just store this into B. So knowing the values of A and B, we can therefore conclude theta is equal to 69.6 minus 51.6 e to the minus 0.07 t. Now for part B of the question, ethanol has a boiling point of approximately 78 degrees C. We have to use this information to evaluate the model. Well, if we take a look at what we have over here, I'm hoping you can recognize that the maximum temperature when T is equal to 0, the initial temperature is the difference between 69.6 and 51.6, and the maximum range will be 69.6, and therefore the model is not appropriate. So we see here that the maximum range is 69.6, which is less than the 78, so the model is not appropriate. Question number 10. For part A, we have to show that cos of 3A is equivalent to 4 cos cubed A minus 3 cos A. Well, to do this question, we can rewrite cos of 3A as cos of 2A plus A. So, for part A of the question, cos of 3A is equivalent to cos of 2A plus A. And using the compound angle formula highlighted here, cos of A plus B is equivalent to cos A cos B minus sin A sin B. We can rewrite cos of 2A plus A. We can rewrite this as cos of 2A, actually we won't need the brackets. We have cos of 2A times by the cos of A minus the sine of 2A times by the sine of A. And we can use the double angle formula. Cos of 2A, that's the same as 2 times by the cosine squared of A minus 1, and then we still multiply this by cos A, so cos 2A is the same as 2 cos squared A minus 1, and then we subtract off sine of 2A. Well, sine of 2A, that's the same as 2 sine A cos A, and then we multiply this by sine A. So sine of 2A is the same as 2 sine A cos A. And if we expand, we see over here we have 2 cos A times by cos A, that's 2 cos cubed A, minus 1 times by cos A, that's minus cos A, and then here we have 2 times by sine A times by sine A, that's minus 2 sine squared A, and then we still have the cos A. So we have 2 cos cubed A minus cos A, and then sine squared, that's the same as 1 minus cos squared. So sine squared A is the same as 1 minus cos squared A, and then we multiply this by cos A. So if we expand out even further, we have 2 cos cubed A minus cos A. 2 times by minus 1, that's minus 2. Minus 2, well, and then we multiply by the cos A. And then minus 2 cos A times by minus cos squared A, that's going to be plus 2 cos cubed A. And if we collect like terms, 2 cos squared A plus 2 cubed cos A plus 2 cubed, 2 cos cubed A plus 2 cos cubed A, that's the same as 4 cos cubed A, and then minus cos A minus 2 cos A, that's minus 3 cos A. So that's our result to part A. And now for part B of the question, hence solve for x being in between minus 90 and 180, the equation 1 minus cos 3x equals sine squared x. Well, we can use what we had in part A over here. So we have 1 minus cos 3x to begin with, and this is equal to sine squared x. So we wish to solve this in between minus 90 and 180. So the cos 3x, using the result over here, that's the same as 4 cos cubed x minus 3 cos x. And this is equal to sine squared x. Now sine squared x we can rewrite as 1 minus cos squared x. The reason I want to do that is because if I have everything involving a cos, that might make life a bit easier for myself. And at this point I'm hoping you can see the ones cancel on both sides, and if we multiply the minus into the bracket, we have minus 4 cos cubed x plus 3 cos x equals minus cos squared x. And if we take everything over to one side, we have 4 cos cubed x minus cos squared x minus 3 cos x equals 0. So at this point we can factorize out a cos x from each term. So we have cos x lots of 4 cos squared x minus cos x minus 3 equals 0. And here we have a quadratic which we can factorize. We can factorize this as cos x. We can factorize this as cos x minus 1 lots of 4 cos x plus 3. And then we still have this cos x over here. And all this is equal to 0. So what we can hopefully see here then, that cos x is either equal to 0, it's either equal to 1, or it's either equal to minus 3/4. And our next step will be to draw the graph of cos x in between minus 90 and 180. So having drawn the graph of cos x in between minus 90 and 180, we see, of course, when cos x is equal to 0, we have a solution here. And we also have another solution here. So when cos x is equal to 0, we see that we have x equals minus 90 and 90. So we have x equals minus 90, and we also have x equals 90. And we also see that when cos x is equal to 1. So when cos x is equal to 1, we have a solution of x equals 0. We can see that over here. So this is our other x value. We have 0. And we also see that when we have cos x equals minus 3/4, well, minus 3/4, if we draw a horizontal line here, say, we have a solution over here. And this solution over here we can quite easily work out. We have over here the inverse cos. Make sure we're in radians first. We have the inverse cos of minus 3/4, which is 139 degrees to the nearest whole number. Okay, so we have 90 degrees, 0 degrees, minus 90 degrees, and 139 degrees as our solutions of x. Question number 11. We have figure 2 over here, which shows a sketch of the graph with equation y equals 2 lots of the mod of x plus 4 minus 5. We've got the vertex p over here, which is shown in figure 2. We have to find the coordinates of p. Well, we can treat this as some sort of a minimum point. We can liken this to a typical quadratic graph. What we mean by that, for part A of the question, if we have y equals a plus the mod of x plus b plus c, we can see here that the vertex has coordinates minus b, c, and therefore the coordinates of p, which is our vertex, has coordinates minus 4, minus 5. For part B of the question, we have to solve the equation 3x plus 40 equals 2 lots of the mod of x plus 4 minus 5. So, first of all, if we write this equation down, we have 3x plus 40 equals 2 times by the mod of x plus 4 minus 5. So, rearranging, we have, if we add 5 to both sides, we have 3x plus 45. This is equal to 2 times by the mod of x plus 4. So what we can now do is divide both sides by 2. And if we do that, we have the mod of x plus 4, which is equal to 3x over 2 plus 45 over 2. Now, to get rid of the mod, we would have a positive and negative. So we have plus minus x plus 4 equals 3x over 2 plus 45 over 2. So if we deal with the positive, we have x plus 4 equaling 3x over 2 plus 45 over 2. So we have 1/2 x, which is equal to minus 37 over 2, and therefore x is equal to minus 37. And if we deal with the negative, we have minus x minus 4 equaling 3x over 2 plus 45 over 2. So we have here 5x over 2, which is equal to minus 53 over 2, and therefore x is equal to minus 53 over 5. And in terms of which solution we take, minus 53 over 5, that's minus 10.6. And if we go back to our diagram, we have over here over here we've got the point minus 4, x equals minus 4. So minus 10 point something, that's over here somewhere. And essentially our solution will look something like this. Now of course this will continue up to the y-axis at the point y equals 40, but what I'm hoping you recognize is here we have our solution of x equals minus 53 over 5. So here we have x equals minus 53 over 5, and therefore our solution, our only solution, is x equals minus 53 over 5. So this is the only solution. Now for part C of the question, a line L has equation y equals ax, where a is a constant. Now straight away you should instantly be thinking to yourself, this passes through the origin. Given that the line L intersects y equals 2 times by the mod of x plus 4 minus 5 at least once, we have to find the range of possible values of a, writing your answer in set notation. Well, if we look over here, if the graph had the equation y equals 2x, because this graph over here, which is the graph of y equals 2 times by the mod of x plus 4 minus 5, this line and this line are parallel to each other. Now, we were told that they intersect at least once, so if we have a steeper gradient than this line here, then that will ensure that we intersect this graph at least once. So in other words, we want something a bit steeper than this, which will intersect. Of course, I'm exaggerating the graph here. This over here is the graph of y equals ax, where of course here a is greater than 2. So one possible solution we have is, for part C, a being greater than 2. That will ensure we intersect the graph at least once. And another way we can intersect the graph is if we have a gradient, say over here, where it intersects over here. Well, actually, it intersects at this point P. So we have something which looks like that. If I draw it neatly, we have something which looks like this. So this is the graph of y equals ax. And of course, the gradient of this red line, that will, well, if this point over here is minus 4, minus 5, we can use the fact that change in y over change in x is gradient. So here we have a change in x which is minus 4, so here we have minus 4, and our change in y, that's equal to 5. So therefore our gradient here is equal to 5 over 4. So one possible value we could have is a being less than or equal to 5 over 4. Because the reason I say less than is because if the gradient is less than this, then still passing through the origin, it could intersect hearsay. So this is why we include the less than. Okay. So, having said all that, we've got a being greater than 2 and also a being less than or equal to 1.25, which is the same as 5 over 4, and therefore in set notation we have the following. Okay, so don't forget the union symbol. So this over here is our solution. Question number 12. The curve shown in figure 3 has parametric equations x equals 6 sine t, y equals 5 sine of 2t, where t is in between 0 and pi over 2. The region R shown shaded in figure 3 is bounded by the curve and the x-axis, and we have to show for the first part of part A that the area of R is given by the integral from 0 to pi over 2 of 60 sine t cos squared t with respect to t. Well, over here we can make use of the formula to integrate parametrically. That is the integral of y multiplied by dx over dt multiplied by dt. Now, before we go any further, I think it will be a good idea to work out what dx over dt is. Dx over dt, if we differentiate our x function with respect to t, differentiating 6 sine t, we end up with 6 cos t. So we have 6 cos t. And if we substitute this into this equation here, we can hopefully see that the region R, that's given by the integral from 0 to pi over 2 of y, which is 5 sine 2t, multiplied by dx over dt, which is 6 cos t dt. So, what we can see here, 5 times by 6, that's 30. So we have the integral from 0 to pi over 2 of 30 sine 2t cos t dt. And sine 2t we can rewrite as 2 sine t cos t. So this result here is what sine 2t is. So we have the integral from 0 to pi over 2 of 30 multiplied by 2 sine t cos t multiplied by cos t dt. So here we end up with 30 times by 2, which is 60. So we have 60 sine t times by cos squared t dt. Okay, and that's what we wanted to show. And now for the next part of the question. Hence, show by algebraic integration that the exact area of R is exactly 20. Okay, so this was for the first part of part A, and for the second part we just have to carry out this integration. So what we can do over here is recognize that the cos squared t we can rewrite as cos t squared. So we have 60 sine t times by cos t all squared dt. And what we can do over here is use the reverse chain rule, because the differential of the bracket, that is cos t, is outside of the bracket. the differential of the bracket, cos t, is minus sine. Of course, we may have to make some sort of adjustments, but what you can hopefully see here is, if I take the 60 outside the bracket, we have over here cos t squared dt. Differentiating this, we get minus sine. So we get minus sine t. So we wish to integrate this between 0 and pi over 2. And because we have a positive 60 here, we have to have a minus 60 here, because the minus and the minus give a plus. So, using the reverse chain rule, where we add 1 to the power and divide by the new power, and then divide by the differential of the bracket, we have minus 60 lots of, if I open up a big bracket here, we have minus sine t times by cos t cubed divided by minus sine t multiplied by 3. And we wish to evaluate this between 0 and pi over 2. And of course, the minus sine t's cancel on both sides. Minus 60 divided by 3, that's minus 20. So what we have over here is minus 20 lots of the integral of cos cubed t, and we wish to evaluate this in between 0 and pi over 2. So for our upper limit, we have minus 20 times by cos of pi over 2 cubed. For our lower limit, we have minus 20 times by the cos of 0 cubed. So if we work this out, cos of pi over 2, that's 0. So here we have 0 minus 20. So therefore, the area of R is equal to 20. And that's exactly what we wanted to show. The area of R is equal to 20 square units. And now for part B of the question, part of the curve is used to model the profile of a small dam, shown shaded in figure 4 over here. And using the model, and given that x and y are in meters, the vertical wall of the dam has a height of 4.2 meters high, and there is a horizontal walkway of width mn along the top of the dam. We have to calculate the width of the walkway, and of course the width is referring to the distance mn. So to do this question, if we find the value of t for which we have a height of 4.2 meters, we can use that to find the corresponding x value over here. So we have our y being equal to 5 sine 2t, and with that we can find out the value of t for which we have this distance over here. So to do that, we need to set 5 sine 2t equal to 4.2. So we have 5 sine 2t equals 4.2, and therefore sine 2t, that's going to equal the 4.2 divided by 5, which is 0.84, and therefore 2t, we're going to end up with two values, so make sure we're in radians over here. We have the inverse sine of this, that's equal to 0.997, etc. So we'll just store this into A for now. And then to find the second value, pi minus this, that's equal to 2.144, etc. We'll store this into B for now. And therefore, to find out the value of t, we would have to divide by 2. So if I divide this by 2, we end up with 1.072, etc. So let's store this into b, and then our value of a, dividing that by 2, we end up with 0.498, etc. Okay, so what we have over here then is, let's store this into a, we have two values of t. And with these values of t, we can then find out what the corresponding x values are going to be. Now, of course, this value here will give the distance directly below n, and the first value will give the value of x from here to here. So when t is equal to 0.498, etc., we have we can use our formula for x. X is equal to 6 times by the sine of t, so we have 6 times by the sine of 0.498. So if we work this out, we have 6 times by the sine of this, which is 2.869, etc. Okay, meters. So let's just store this into C. And when t is equal to 2.144, etc., x is equal to 6 times by the sine of 2.144, etc. So we have 6 times by the sine of, I think it was b. Turns out we get 5.269, etc. meters. And so the difference between these is the width. So therefore, the width, that's going to equal 5.269, etc. minus the 2.869, etc. So working this out, we have over here this value, subtract this value of c. So subtract off c, turns out we get 2.4 meters. So we have 2.4 meters. Question number 13. A function g is defined by g of x equals 3 times by the natural log of x minus 7 over the natural log of x minus 2, where x is greater than 0 and x doesn't equal k, and k here is a constant, and we have to deduce the value of k. Well, for us to do this question, we need to think to ourselves what value of x makes the bottom equal to 0, and therefore we don't want that value of x, otherwise we'd be dividing by 0. So to do that, we can simply set the bottom equal to 0. So here we've got the natural log of x minus 2 equals 0. So if we solve for x, we've got the natural log of x equaling 2, and therefore x is equal to e to the power of 2. And therefore x cannot equal this value, otherwise we'd have an otherwise we'd be dividing by 0. So therefore x cannot equal e to the power of 2. In other words, k is equal to e to the power of 2. So this over here is our vertical asymptote. Let's just write this down. So x equaling x squared is the vertical asymptote. And now for part b, we have to prove that g dash of x is greater than 0 for all values of x in the domain g. So the fact that we've got a g dash suggests to us we need to differentiate. So we need to differentiate this rational function, and we can do that using the quotient rule. And if we use the quotient rule for part b, u is equal to the thing at the top, 3 times by the natural log of x minus 7. V is the thing at the bottom, the natural log of x minus 2, u dash that's equal to 3 over x, and v dash that's equal to 1 over x. So if we apply the quotient rule, g dash of x, that's going to equal v u dash minus u v dash all over v squared. So let's substitute in everything we know to figure out what g dash of x is. So g dash of x, that's going to equal v, which is the natural log of x minus 2, times by u dash, which is 3 over x, minus u, which is 3 times by the natural log of x minus 7, times by u dash, which is 3 over x. And on the bottom we've got v squared. So on the bottom we've got the natural log of x minus 2 all squared. So if we expand on the top, 3 over x times by the natural log of x, that's just 3 ln x over x, minus 2 times by 3 over x, that's minus 6 over x. And then here, minus 3 ln x, sorry, here we've got 1 over x. 3 ln x times 1 over x, that's minus 3 ln x over x. And then minus and a minus, that gives a plus. 7 times by 1 over x, that's just 7 over x. So on the bottom, we've got the natural log of x minus 2 all squared. So if we simplify on the top, you can see here, this term and this term cancel out. Minus 6 over x plus 7 over x, that's just 1 over x. And on the bottom, we've got the natural log of x minus 2 all squared. And if we bring this x to the denominator, we've got 1 over x times by the natural log of x minus 2 all squared. And we want to show that this is greater than 0. And it should be obvious how this is greater than 0. We know 1 is greater than 0. We know from the question x is greater than 0. And the natural log of x minus 2 all squared, that's going to be greater than 0 because something squared is greater than 0. Now at this point you probably think, why is it not equal as well? The reason for that, if it was equal to 0, we'd be dividing by 0. And because all the terms are greater than 0, we can therefore conclude g dash of x is greater than 0. Part C of the question, we have to find the range of values of a for which g of a is greater than 0. Now, what we can do over here is think to ourselves, how can we go about sketching this graph over here? Now it is a bit complicated, but you should be able to recognize we have a rational function which we need to sketch. And that will help us determine the values of a for which g of a is greater than 0. And we know already we've got a vertical asymptote at e to the power of 2. So if we make some sort of an attempt to sketch the graph, we've got a set of coordinate axes, and we know already we're going to have an asymptote over here somewhere. Okay? So here is where we're going to have an asymptote at x equals e to the power of 2. And what we also know is it's a rational function, so the graph is going to look something like this. Okay? And I'm not bothered about my horizontal asymptote because I'm just interested in the x values. And notice over here, the graph doesn't touch the y-axis. In other words, it doesn't. When x is equal to 0, y is going to be undefined. And the reason for that is if we take a look back at our original equation, when x is equal to 0, the natural log of x is going to be undefined. So therefore the graph is not going to cross the y-axis. Now we're looking at where the graph is greater than 0, and it's greater than 0 here and also in between these values here. So what we can now do is find out this critical value here, and we can do that by setting g of a equal to 0. So, well, actually let's set g of x equal to 0 to find the critical value. So to find the critical value, which is this point over here, we have 3 times by the natural log of x minus 7 over the natural log of x minus 2 equaling 0. So we've got 3 times by the natural log of x minus 7 equaling 0. Natural log of x equaling 7 over 3. So therefore x is equal to e to the power of 7 over 3. So this critical value here is x equals e to the power of 7 over 3. And we're looking at where the graph is going to be greater than 0, so hopefully you can spot when the graph is, when g of a being greater than 0 occurs at the following points in between 0 and e squared. So a is going to be in between 0 and e squared, and it's also going to be anything beyond the point x equals e to the power of 7 over 3. So we have a being greater than e to the power of 7 over 3. So that's our final answer, and it's quite difficult to spot that in my opinion, but sometimes it might help to draw a rational function first to figure out the required range of values you need. Question number 14. A circle C with radius r lies only in the first quadrant, and it touches the x-axis and it touches the y-axis, and the line L has equation 2x plus y equals 12, and for part A we have to show that the x-coordinate of the points of intersection of L with C satisfy this equation: 5x squared plus 2r minus 48 lots of x plus r squared minus 24r plus 144 equals 0. And at this point I think it will be a good idea to draw a quick diagram to help illustrate what this question's on about. So we've got our circle here. It's got a centre at r, so therefore the radius is r, and I hope that's quite obvious why the radius is r. And then we've got that circle intersecting this 2x plus y equals 12. So we can see that from the diagram. Now we've got the equation of C, which is x minus r all squared plus y minus r all squared equals r squared. That's obvious. And we've got the equation of L, which I'm going to rewrite as y equals 12 minus 2x. Now if I call this equation 1 and this equation 2, if I expand out equation 1 and then substitute this into that expanded equation, let's see what we get. So from 1 we've got x squared minus 2xr plus r squared. Okay, so that's this bracket, and then we've also got over here y squared minus 2xy plus r squared equals r squared. And if we tidy all this up, let's see what we get. Well, we've got here x squared plus y squared minus 2xr minus 2. So this is 2yr, sorry. Minus 2yr plus r squared equals 0. And if I call this equation 3, we can now substitute this equation here into this equation here. So we will now substitute in equation 2 into equation 3. And if we do that, we've got x squared plus y squared, so here we've got 12 minus 2x all squared, minus 2xr minus 2yr, so here we've got 2 lots of, well, I'll just write this as 2r lots of 12 minus 2x plus r squared, and all this is equal to 0. So I've got x squared plus 144 minus 48x plus 4x squared minus 2xr minus 24r plus 4rx plus r squared equals 0. And if I collect like terms, we've got 5x squared minus 48x plus 2xr plus r squared minus 24r plus 144 equals 0. And therefore, in conclusion, we have over here 5x squared 5x squared plus 2r minus 48 lots of x plus r squared minus 24r plus 144 equals 0. And that's exactly what we wanted to show for part A of the question. And now for part B of the question, given also that L is a tangent to C, we have to find the two possible values of R, giving it answers as fully simplified surds. Well, because we've got L which is a tangent to C, what we can say from here is the following. If L is a tangent to C, b squared minus 4ac is equal to 0, so the discriminant is equal to 0. And I think at this point it will also help to draw a diagram to help illustrate what this question is requiring us to do. So we've got two possible situations. We've got a circle here or a circle here. And we've got this tangent over here, okay? So that's basically what the question's saying. There's two possibilities of R. We can either have R over here like this. So here we've got a short radius of R, or we've got a larger radius like so. And our job is to find these two possible values of R. And we've also got this straight line over here. We've got the equation here, 2x plus y equals 12. And here it crosses at 6 and 12. So if we use the discriminant, we see over here a is equal to 5, b is equal to 2r minus 48, and c is equal to r squared minus 24r plus 144, and all this is equal to 0. So that's just using the values of a, b and c. So if we use the discriminant and set that equal to 0, we've got b squared, so here we've got 2r minus 48 all squared minus 4 lots of a, which is 5, lots of c, so here we've got r squared minus 24r plus 144, and all this is equal to 0. So if I expand and simplify, 4r minus 48 all squared, that's 4r squared minus 192r plus, well, here we've got 48 squared, which is 2304. And then here we've got minus 20r squared plus 480r minus 20 times by this, which is 2880, and all this is equal to 0. So if I collect like terms, we've got minus 16r squared plus 288r minus 576 equals 0. And if I divide everything by minus 16, it turns out we get r squared minus 18r plus 36 equals 0. And if we solve this using our calculator, we've got r squared minus 18r plus 36. So the two possible values of r we've got is 9 plus minus 3 root 5. So that's our final answer. Question number 15. A geometric series has common ratio r and first term a, and given that r doesn't equal 1 and a doesn't equal 0, we have to prove that Sn is equal to a lots of 1 minus r to the power of n over 1 minus r. Now, a geometric progression, GP, that has formula un equals ar to the power of n minus 1. And if we use that, for part A of the question, our first term, when n is equal to 1, we have a times by r to the power of 1 minus 1. So we have a times by r to the 0. R to the 0 is simply 1, so we have a times by 1, which is a. Our second term, when n is equal to 2, we have ar to the power of 2 minus 1, so we have ar. Our third term, u3, that's equal to ar to the power of 3 minus 1, so we have ar squared. When n is equal to 4, u4 is equal to ar to the power of 4 minus 1, so we have ar cubed, and we can continue this. And the second to last term, that's going to equal, well, let's start off with the last term. The last term, when we have un, that's going to give us the last term being ar to the power of n minus 1, and the term before this, that's going to be ar to the power of n minus 2. Now, for a sum, we simply add all these terms together. So, if we add those terms together, we have our first term a. Now I'm going to write these in a square bracket. We have first term a, second term ar, third term ar cubed, and we can continue this. Continuing, we have ar to the power of n minus 2, and then we've got over here ar to the power of n minus 1. So if we now multiply both sides by r, we have r Sn equals, if I multiply all these by r, a times by r, that gives ar, ar times by r, that gives ar squared, ar cubed times by r, that gives ar to the 4, and then we can continue this, ar to the power of n minus 2 multiplied by r, that gives ar to the power of n minus 1, and finally ar to the power of n minus 1 multiplied by r, that gives ar to the power of n. So with that, we can now subtract these equations. So if I call this equation 1 and this equation 2, we can subtract these equations. So if we do 2 minus 1, we have r times by Sn minus Sn, and this is equal to, well, here we've got ar minus a, and then we've got ar squared minus ar, and then here we've got ar to the 4 minus ar cubed, etc. So you can see these terms match up. So if we subtract these from each other, what we have over here then is this term cancelling with this cancelling with this cancelling with this cancelling with this. Essentially we are left with over here ar to the power of n minus a. And if we now factorise on both sides, we have Sn lots of r minus 1, and this is equal to a r to the power of n minus a. So if I factorise on this side, hopefully you can see we have a lots of r to the power of n minus 1, and if I divide both sides by r minus 1, Sn, that's going to equal a lots of Rn minus 1 over r minus 1. So therefore Sn is going to equal a lots of 1 minus r to the power of n divided by 1 minus r. And now for part B of the question, given also that S10 is 4 times S5, we have to find the exact value of r. So for part B of the question, what we have over here is S10, which is equal to 4 times by S5. So S10, that's going to equal a multiplied by 1 minus r to the power of 10 over 1 minus r, and this is equal to 4 lots of a lots of 1 minus r to the power of 5 divided by 1 minus r. And essentially here, this a cancels with this a, and this 1 minus r cancels with this 1 minus r. So we have 1 minus r to the power of 10 equals 4 lots of 1 minus r to the power of 5. If we expand and simplify, we have 1 minus r to the power of 10 equals 4 minus 4r to the power of 5. And if we take everything over to one side, we have r squared minus 4r to the 5 plus 3 equals 0. And I hope at this point you can recognize we have a hidden quadratic. Of course, here we have the r to the 5 term. Sorry, here we've got an r to the 10. So let's make sure I've wrote the right thing down. So r to the 10 we can rewrite as r to the 5 squared. So we have r to the 5 all squared minus 4 lots of r to the 5 plus 3 equals 0. And to solve this quadratic, we can make a substitution. For example, we can let t equal r to the 5. And if we do that, we have t squared minus 4t plus 3 equals 0. Factorising, t minus 1 lots of t minus 3 is equal to 0. So we've got two possible solutions. We've got t equals 1, t equals 3. And using r to the 5, we've got r to the 5 which is equal to 1, and we've got r to the 5 which is equal to 3. And we know that r cannot equal 1, so therefore r to the 5 cannot equal 1, because taking the fifth root of 1 we still get 1. So therefore our only solution in exact form is the fifth root of 3. So this is our only solution. Question number 16, we have to use algebra to prove that the square of any natural number is either a multiple of 3 or one more than a multiple of 3. And the key in this question is to recognize natural numbers can be written as 3x, 3x plus 1, or 3x plus 2. And if we get that far, if we now square these numbers, so in the first case if we square the 3x, we have here 3x all squared, and if we work this out we get 9x squared, which is the same as 3 lots of 3x squared. Okay? And what we see over here, 3 lots of 3x squared is a multiple of 3. Let's consider the case of 3x plus 1. So if we have 3x plus 1 and then we square this, well, what we have over here is 9x squared plus 6x plus 1. Okay? And if we factorize out a 3 from the first two terms, we have 3 lots of 3x squared plus 2x plus 1. So we have something which is one more than a multiple of 3. And if we consider this 3x plus 2 all squared, so if we have 3x plus 2 all squared, this is the same as 9x squared plus 12x plus 4. So we can rewrite this as 9x squared plus 12x plus 3 plus 1. The reason I want to show this, if I can show that this is one more than a multiple of 3, a multiple of 3 can, if we can somehow factorize out with 3, then we've shown that this 4 can be written as 3 plus 1, which will help us to factorize. And if we do that, we have 3 lots of 3x squared plus 4x plus 1 plus another 1. So this result here is one more than a multiple of 3. So any natural number is either a multiple of 3 or one more than a multiple of 3.